Good morning everyone. The next important topic in power system operation and control, that is unit 3, the modeling of various components of generating plant including speed governing system. It might be video number 15 approximately. Now let me explain the basic control loops of power system. There are two basic control loops, AVR and ALFC. AVR is the automatic voltage regulator, or QV loop, reactive power and voltage loop. The second one is ALFC loop, automatic load frequency control loop, or power and frequency loop, PF loop. These are the basic control loops of generating plant. So the first one is turbine generator set is there. The turbine and generator both are coupled together. So these two are coupled, and the generator is generating the three-phase electrical power connected to the bus bars. ABC is the phase sequence of generator. So from the output terminals of generator, using voltage sensor, you can measure the voltage, and that voltage is given to the QV controller, so that from the QV controller you will get the delta Q. Delta Q is given to the excitation system. So this delta Q will change the excitation settings, so that it will control the voltage. Why? Because Q and V both are strongly related. We will establish that relation later. So this is the AVR loop. The very first one is AVR loop. You can have second loop. That second loop is frequency control loop, inner control loop of the load frequency loop. So there are two control loops in the ALFC. Very first one, let us understand this. From the output terminals of the generator, you can sense the frequency. This frequency, the output of the frequency is delta F, change in frequency due to change in load. So this delta F is given to the PI controller, so that this PI controller will control the valve mechanism, so that the steam admitted to the turbine can be changed by using steam valve control. So this is the steam valve control. By using this control, we can change the steam input of the turbine, and hence the power output of turbine PT can be changed. Power output of the turbine PT can be changed. When PT changes, PG also changes, active power. Therefore it is termed as PF control. So this is the second loop in our discussion. These are the two basic control loops. Two basic control loop of generating plant, particularly steam power plant. The same thing is shown here also. You can see the generator. The turbine is rotating the generator. So therefore the mechanical input is given to generator. Generator will produce the electrical power output, from which you can have the AVR. This is the AVR loop. So this is the ALFC loop. The same thing is shown here, delta V and given to QV controller, and delta Q is obtained, from which you can control the field. Similarly here, delta F is given to PI controller. So this is the delta P type. power required by the other control area. This is the PI controller. So, valve mechanism through which you can control the steam injected to the turbine. So, this is one what we have considered. This is 2. This is 2. Okay, these are the basic control loops. This is the first loop of ALFC. Coming to the second loop of ALFC, you can look at this figure, 3-dimensional. The same thing is illustrated again. This frequency is sensed here, compared with the signal mixer here, tie line power, delta P tie. So, this is delta F, this is delta P tie. So, this is integrated PI controller again, speed changer, from which you can get the delta P reference. This is the secondary control loop. This is the secondary loop. So, this is secondary loop. ALFC loop. Primary loop already you have seen. This is the loop number 1. This is 2, primary loop. This is 3, third loop. It is also known as secondary ALFC loop. Secondary ALFC loop is slow and it is passed through the slow acting integrator, so that the dynamics of the first loop and second loop both will be settled. Both will be settled. The first loop is faster than 2, second loop is faster than 3. So, in serial, the action of the first loop will be completed first. The action of the second loop can be completed before the action of third loop commences. Therefore, the slow acting integrator will allow the system to settle down to a steady state value with the help of AVR and primary ALFC loops. So, this is the added advantage of your ALFC loop, secondary loop. If you have the primary ALFC loop, why do you go for secondary ALFC loop? So, within the control area, if any dynamics are required, the primary ALFC loop, also known as AGC, automatic generation control. So, AGC will take care of your control area requirements, and the secondary loop will give you the zero steady state error, as well as it will take care of other area requirements with the help of P tie, delta P tie. So, the interchange between control areas can be facilitated with the help of secondary loop. The same thing is illustrated in the words by using words. QV loop or AVR loop, it controls the terminal voltage of the generator. Very first one, voltage is continuously sensed and rectified and smoothened with the help of rectifier and filters. This DC voltage is compared with the V reference, which will give the error delta V. So, this delta V controls the terminal voltage, which will leads to delta Q. So, this delta Q is used to control the field current. So, that is delta IF, field current, which will control the delta V again, or terminal voltage. The second one is slow ALFC loop, primary loop. So primary loops will take care of speed and frequency variations. This is the second loop. Second loop, it maintains the megawatt interchange between other pool members, other control areas. This is third one. So already you understood in the figures. The same thing is mentioned here in words. Up to that everybody understood. Now let me explain speed governing system, turbine speed governing system. In the speed governing system, so very first one is speed changer. This speed changer will have rise command and lower command. The last one, this is the control valve. This control valve is related to point E. ABC is the pivoted rigid link, pivoted at point B, and CDE is another rigid link pivoted at point D. So this D is connected to the pilot valve here, and E is connected to this main control valve. So the points A, B, C, D, E movements are termed as delta XA, delta XB, delta XC, and so on, delta XC. All these displacements are equivalent to power variations. Why? Because this valve movement related to displacement delta XC, and that valve movement is related to power output, variation in the power output. How? So when the valve comes down, the more steam is admitted to the turbine. When more steam is admitted, the power output of the turbine delta PT increases, and vice versa. So therefore the movements of the points, linkage points, are related to power variations. Power variations. Here delta XA related to delta P reference, delta XC related to delta PV, valve power output. Similarly, delta XC related to delta PG, governor output power. Delta XB related to delta F, frequency variation. This is the speed governor. The speed governor will have balls. These balls will move outwards and inwards based on speed variations. And here hydraulic amplifier is used to increase the power level of low power piston valve movement into high power main valve movement. Can be converted or can be achieved with the help of hydraulic amplifier. Okay. So therefore the very first one, speed changer. When the speed changer is there, when you give the rise command, due to rise command delta XA will comes down. Delta XA comes down. This rise command will leads to downward movement of XC, so that more steam is admitted and power generation can be increased with the help of rise command. These two are related like that, and vice versa. When lower command is given, delta XC movement will be upwards and less steam is admitted to the turbine, and power output of the turbine can be decreased. This is the rise and lower command related to P reference. Delta XA movement related to P reference. Therefore, P reference is increased, power generation must be increased. P reference is decreased, power generation must be decreased. With the help of linkage mechanism, this can be achieved. So, coming to the next point, when the frequency increases, phase ball movement comes outwards. So, therefore, frequency increases in the sense the load on the system is decreased. Therefore, the frequency is increased. When the frequency is increased, the power generation must be decreased to balance the load, so that the frequency can be controlled. So, when the frequency is increased, outward movement of the balls leads to decrease in the steam input to the turbine, and hence the decrement in the power generation Pg. The hydraulic amplifier is nothing but the ordinary amplifier, like our power amplifier. It will amplifies the fluid signals. So, the same thing is illustrated here also with the printed figure. Rise and lower commands. Rise command will give the increase in Pg, lower command vice versa. Similarly, the outward movement of the balls, so when delta F increases, leads to delta Pg decreases. This is the second point. First point, this is second point. So, high pressure oil is coming here. This is the pilot valve and this is the main valve. This main valve movement is measured with the help of Xe, delta Xe, delta Xd, delta Xc, and so on. This is the linkage mechanism. Already you have seen. So, what is the speed governing system? What are the components, and what is the significance of each of the components? Fly ball speed governor, when the speed is increased, frequency also increases. Fly ball move more outwards, leads to point B, moves downwards, and vice versa. This is the first point. Second point, hydraulic amplifier. It converts the low power pilot valve movement to high power piston valve movement. So, it is necessary in order to control the steam valve against the high pressure steam. Sometimes several stages of the hydraulic amplifier are also cascaded to increase the power level. This is very important point. Third one, linkage mechanism. ABC is rigid link pivoted at point B. CDE is another at point D, pivoted at point D, fixed at point D and point B. So, it provides the control valve movement in proportion to the change in speed, and also provides the feedback to the valve movement. Last one, speed changer. It provides the steady state power output setting for the turbine. So, downward movement of the speed changer increases the steam admitted to the turbine and hence the power output. These are the points already explained. Now, let us have speed governing system. Delta Xc is the downward movement, leads to delta PV upward, increase in the valve output and turbine output, generator output, and vice versa. Second point. So, and first here is the point, the position of the pilot valve can be affected via the linkage mechanism. The very first one, delta x, a downward movement, leads to delta P reference, increase in the delta P reference, and vice versa. The second one, indirectly via the feedback. Third one, indirectly via the feedback due to changes in xb with the speed changes. Now, rise command to the speed changer leads to increase in delta pt and delta pg. Lower command decreases the delta pg with the help of linkage points A, B, C, D, 5 points. So, linkage point moments are in millimeters mm. So, both are related with megawatts variation in the power. Therefore, mm and megawatts both are related, are per unit megawatts. So, all the movements of the points are measured with arrow directions. So, delta Pg is measured by delta Xc. It has two inputs. What are the two inputs? Governor inputs are delta P reference, second one is delta F is measured by delta Xb. Delta P reference is increased, delta Pg also increases. Delta F decreases, delta Pg also increases. So, therefore, for small increments, let us formulate in equation delta Pg and related to delta P reference, directly related to delta P reference. Therefore, delta Pg equal to delta P reference, a positive sign. Let us use positive sign here. Here it is negative sign. Delta P reference minus some constant into delta F. That constant is 1 by R. R is the droop. That droop is nothing but heads per megawatt. Droop is nothing but regulation or slope. When the load on the machine increases, because of the droop, the frequency falls down, and vice versa. So, therefore, the final equation delta Pg of S equal to delta P reference of S minus 1 by R into delta F of S. So, these two are important points. Delta Pg proportional to delta P reference and inversely proportional to delta F. Inversely proportional can be taken as negative sign. So, therefore, delta Pg equal to delta P reference minus 1 by R into delta F. This is the governor inputs. The part of the governing system is hydraulic amplifier, one of the important one. Delta xd, there is increment in the delta xd, movement, upwards movement leads to delta Pg, increase in the delta Pg, and downward. So, therefore, the downward movement of xd related to delta Pv, there is increment in delta P. Therefore, equal increase in delta Pg and delta Pv leads to xd equal to 0, delta xd equal to 0. And for the small changes of delta xd, oil flow into hydraulic motor is proportional to delta xd, and hence delta Pv equal to so proportionality constant kh into integral of delta xd dt. So, therefore, gh of S, transfer function of the hydraulic amplifier, is delta Pv by delta Pg, that is equal to 1 by 1 plus S into Th is the transfer function of hydraulic amplifier, where Th is equal to 1 by Kh. So, integral Kh into xd of S. Integration is 1 by S. Kh into 1 by S into delta xd. So, by using that, you got gh is the transfer function of hydraulic amplifier, that is equal to 1 by 1 plus S into Th is the hydraulic amplifier transfer function. Now, this is the governor inputs equation, hydraulic amplifier. Next one, turbine transfer function, and generator load model. So this is the first equation, delta F into 1 by R is the negative sign, delta P reference minus 1 by R into delta F equal to delta PG. Delta PV by delta PG equal to GH. GH is already derived, 1 by 1 plus S into TT. TH, hydraulic amp. Therefore, that can be treated as TH or TG, speed governor system. So therefore, this is the turbine transfer function. Previously we have discussed that turbine transfer function. So TT is typical value is 0.2 to 2 seconds. TR is 10 seconds, around 10 seconds. Regulation or droop is 5%, less than or equal to 5%. TH or TG equal to 0.1 seconds. And KR is equal to 1 minus fraction of the reheated speed. So this is the transfer function model of speed governing system including turbine. So I will stop here. Thank you, one and all.